is invertible, what does that tell you about the determinant of A? Not equal to 0. That was a little bit tricky. You could have written equals non-zero. Oh, that's true. Yeah. If A is invertible, the determinant of A also equals the determinant of A transpose.
So that is okay as well?
Yep.
Okay. What is so for -1 to the R start the product of pivots?
That is true. Yep. Yep. The formula given in the book, you could use that. The determinant of A is equal to -1 to the R times the product of the pivots from any echelon form, right? Yeah, sure, I'll take that. This is if A invertible. And if A is not invertible, the determinant of A is 0. Okay, so more answers than I expected are possible. So that's the formula the book gives, or you could write equals non-zero, or the determinant of A equals the determinant of A transpose. Okay, so yeah, multiple choice. If 0 is an eigenvalue of a square matrix, then the matrix is invertible or not invertible? Not invertible. And what is the characteristic equation of a matrix A? Close. It's the determinant of A minus lambda I equals 0. You said determinant? Oh, sorry, I didn't hear you. All right, so today we're going to talk about how to find eigenvalues without first being given an eigenvector. So last class we could check, is this vector an eigenvector? Is this value an eigenvalue? And if you determined that something was an eigenvector or an eigenvalue, then you could find the associated value or vector that goes with it. But today we're going to find eigenvalues without knowing an eigenvector first. All right, so to find eigenvalues of a matrix, we go to the definition of an eigenvalue we learned last class. You're searching for all scalars lambda such that A minus lambda I times the vector x equals 0. Has a non-trivial solution. Any lambda that you could put in there that makes this equation have a non-trivial solution is an eigenvalue. That's the definition. But the invertible matrix theorem says that saying a matrix equation has a non-trivial solution is equivalent to saying that the matrix is not invertible, right? So that was one of the 15 things in the invertible matrix theorem. If AX equals 0 has a non-trivial solution, A can't be invertible. So in this case, it's not A, it's A minus lambda I, right? So A minus lambda I is not invertible, and a matrix is not invertible when its determinant is 0. So to find the eigenvalues, we solve the equation, the determinant of A minus lambda I equals 0. And that equation is called the characteristic equation of the matrix A. And if you take off the equation part, just the determinant of A minus lambda I without the equals 0, we call that the characteristic polynomial of the matrix A. And the algebraic multiplicity of an eigenvalue lambda is its multiplicity as a 0 of the characteristic polynomial. So we talk about this in like college algebra. The multiplicity of a 0 is just the number of times it comes up as a 0. Okay, so to use all of this stuff, the characteristic equation, all has to do with determinants. It all rests on being able to find a determinant. And luckily, we learned how to do that in chapter 3. Okay, so to use all of that stuff about the characteristic polynomial, you need to remember some stuff about determinants. So the determinant of A, you can do by getting A into an echelon form and taking the product of pivots in any echelon form of A. And then it's either a positive or a negative depending on how many row interchanges you did, row swaps, right? Each time you swap a row, the determinant changes sign. That's the R. That's R is the number of row interchanges. Yeah. So if you do 1, it becomes negative. If you do 2, it goes back to positive. And that's a theorem that we learned and used in section 3.2. You also could use a cofactor expansion to find a determinant, also from, I think, 3.1 or 3.2. And we'll do a little bit of that today. And we're going to let A and B be n by n matrices, and then we have several properties of determinants that we already know. The determinant of a product is the product of the determinants. The determinant of A transpose is the same as the determinant of A. If A is triangular, then the determinant of A is the product of the entries on the main diagonal. And a row or column replacement operation on A does not change the determinant, right? So we don't typically do column operations, but you can in doing determinants. And so if you do a row or column replacement, that is when you do a multiple of 1 plus another to replace, that doesn't change the determinant. If you do a row or column interchange, the sign of the determinant changes, and a row or column scaling also scales the determinant. So this is from like several weeks back. It's just reminding you. All right, so we can also add to the invertible matrix theorem that A is invertible, is equivalent to 0 is not an eigenvalue of A. So if you think about determinants, if you have a triangular matrix, its determinant is the product of the diagonal entries, right? And if one of those diagonal entries is 0, the determinant will be 0, meaning the matrix is not invertible. But those diagonal entries also represent the eigenvalues of the matrix, which we talked about last class. So if one of the eigenvalues is 0, the determinant will be 0, and the matrix is not invertible. All right, and then there's this one last little bit in the chapter. A is similar to B if there exists an invertible matrix P such that P inverse AP equals B. And I actually gave you a proof about that statement on your last test. So I don't know if you'll remember, but you'll prove it again today. If A and B are similar, then they have the same characteristic polynomial and hence the same eigenvalues. You'll prove this, or you'll do part of the proof in the activities today. But be careful, just because two matrices have the same eigenvalues does not mean they're similar, right? If they're similar, they have the same eigenvalues, but it doesn't go backwards. Same eigenvalues doesn't tell you they're similar. And then one of your homework problems, number 18, you'll learn from that the dimension of the eigenspace associated with any eigenvalue lambda is always less than or equal to the algebraic multiplicity of lambda. The number of times lambda is a 0 of the characteristic polynomial. Okay, so quick demo. We've got a matrix A, -1, 4, 1, 2. Find the characteristic polynomial. So the characteristic polynomial is the determinant of A minus lambda I. So first, let's calculate A minus lambda I. So A is -1, 1, 4, 2. Lambda times the identity would be lambda 0, 0, lambda. So when I do the subtraction, I get -1 minus lambda, 4, 1, and 2 minus lambda. So that's A minus lambda I. I have to take the determinant of that thing. So remember that the square bracket, if you don't put the little feet on the brackets and you just do like absolute value bars, that means determinant. And then the determinant of a 2 by 2 matrix, AD minus BC. So I'm going to have -1 minus lambda times 2 minus lambda minus 4 times 1. just AD minus BC, and then I can multiply this out. So I have -2 plus lambda minus 2 lambda plus lambda squared minus 4. Combine like terms. So I have lambda squared minus lambda minus 6. That is the characteristic polynomial for the matrix A. The determinant of A minus lambda squared. So this is why it's called the characteristic polynomial. Once you take the determinant of A minus lambda I, it always comes out as a polynomial. So if I want to find the eigenvalues of A, we just set the characteristic polynomial equal to 0 and solve. Yeah, so this factors to -3 plus 2. So we get lambda is -2 and 3. 2 lambda values, -2 and 3. What is the multiplicity of lambda equals -2? Oh, sorry. Yeah, it's 1. Both of these lambdas have a multiplicity of 1. The way you'd get a multiplicity of 2 is say this factored to x minus 3 times x minus 3. Then 3 would be an eigenvalue with a multiplicity of 2.